Hi everybody, welcome to the next lecture on computer animation, this time about textures. So the purpose of textures, apart from putting a texture on the object, is for instance to also add details without increasing the complexity of the geometry, like the modulation of surface properties, so giving it certain roughness, for instance. Most common we have color and brightness, and the analogy here is a wallpaper on the wall or glued photos, and we have those possibilities to modulate the surfaces, for instance with bump mapping. This is a 3D impression by modulation of the surface normals, so basically we change the way that light is reflected. Then we have displacement mapping. This is a change of the geometry using the texture. Then we have procedural texturing. This is a texture, generating a texture according to an algorithm. And then we have volume textures, which are not only on the surface, but also in the volume. So more on this now. So in textures, we have a local coordinate system, UVW. So this is if we have three-dimensional textures. But for 2D textures, like pictures, we only have two coordinates, U and V, because it's just 2D. And usually we have the coordinates from the lower left-hand corner, which has the coordinates 0, 0, to the upper right-hand corner with the coordinates 1, 1. So this is a normalized texture coordinate system. And if we have coordinates larger than 1, we just repeat from 0. And we connect vertices of the object with texture coordinates on our texture image. So this is how we map them or connect them. So here's an example. On the left we have a texture image, which you can see here. And then we use 3 points, T0, T1 and T2, which we then connect to our object. So on the right hand side you see this triangle, this polygon with 3 vertices here, V1, V2, and then there's another one here. And we simply connect these points in our texture to the vertices here. So this is basically how you can then map it. So you can see here, this triangle here is then projected on our polygon, our triangle here on the right hand side. Yeah, so if you have planar pieces like this triangle, this is easy to map, but if we have say a sphere, then it's not so easy. So there are different ways to project. So what we just saw was the planar projections, but there's also a spherical projection and a cylindrical projection. Right, so here we have a sphere, so we would have a spherical projection, but there's also a cylindrical. So if you have, imagine you have your texture on the cylinder, then it's mapped on similarly shaped objects in 3D. Yeah. But this mapping can also result in aliasing, because the required texture resolution depends on the size after projection. So imagine we have an object, we map texture on it, and then we have a close-up of this object. That shows that in this case we would need a high-resolution texture image in order to avoid us seeing pixels, for instance. So usually there is no one-to-one mapping of texture pixels on the rasterized image, meaning for our virtual camera and displaying on our display. So we need interpolation or filtering. And the simplest of these interpolations or filtering is the so-called nearest neighbor approach. In OpenGL it's called GL nearest, and this simply selects the nearest texture pixel to our virtual camera pixel. But nearest neighbor can also lead to alias artifacts because we simply have to select one pixel out of the image And this can lead to moire artifacts in the case if we have many more pixels on the display, as for instance in our texture image. So simple solutions here are low-pass filtering. Very simple low-pass filtering is a so-called bilinear filter, which results from a box filter, which we already saw with the interpolation, right? Our interpolation, linear interpolation is basically convolution with a box filter. And in OpenGL, this is called GL linear. Somewhat more sophisticated is a Gaussian filter. So this is where the kernel is, the filter kernel is not a box function, but a Gaussian function. Then we have anisotropic filtering. This takes better care of texture distortions, like if you have perspective projections, where pixel in a distance, or if you have a tilted surface, then those pixels don't look square anymore. Then we have mip mapping. This is a pre-filtering of the texture at different resolutions, and this is useful for real-time systems because then you just look up the suitable texture in memory. Yeah, so more on this now. So first, the bilinear filtering or box filtering. This is a linear interpolation between adjacent color values of our texture. And the filter matrix or filter kernel or filter impulse response can be displayed as a square or the box. So this should be actually a kernel, not really core, kernel. Okay. So this is the least computational complex low-pass filter, but it also only results in moderate quality. Then we have the Gaussian filter, where the filter kernel represents the Gaussian distribution. So again, this should be kernel. Okay. Here we have a higher computation complexity because this function is more complex, but it results in a better quality. Then we could also take sinc functions, for instance. So remember, a sinc function is simply the impulse response of an ideal low-pass filter, but the sinc function is even more complex. Yeah, so anisotropic filtering is interesting for our objects because texture pixels usually change their shape through projection, so often through perspective. So this should be an R, through perspective. And anisotropic filtering hence works with non-square filter kernels, right? So basically it adjusts its filter kernel to the perspective of the object, thereby taking into account the shape of the projected pixels. This results in very good quality, but also in high computational complexity because we need to adjust the filter kernel all the time. Here's an example. Here on the left you have the anisotropic filter. On the right there's no anisotropy. So you can see when we have no anisotropy, then it's blurred, particularly here in the back, because we don't take into account that the pixels here in the back become much smaller. Here we adjust our kernel according to the pixel size, and that also leads to sharper patterns here in the background. Yeah, here an example for mip mapping. Here we have a level of detail for textures. That means the texture is stored in different resolution levels, as you can see here. High resolution of the space station, and then you have a few more at lower resolutions. So down here it's basically just a dot. This is how you would see it on the sky when it passes over you. So that means the texture is stored in different resolution levels, and the reduced resolutions are filtered to high quality each. Right, so here you can see high resolution. Rendering selects the level that best fits your needs. low filter effort for rendering as a result, right? You just look up in memory. But that also means you have an increased memory requirement, roughly plus 1/3, which you can see here. So these are additional images which you need to store. And this is particularly suitable for real-time applications. And to limit the number of images to store, you apply a so-called trilinear filtering, which is an interpolation between bitmap resolution levels. So you can imagine trilinear because you have 2 dimensions in the image, and then there's the 3rd dimension across the different resolutions here, so that you have the best resolution or the fitting resolution for your object. Yeah, here an example. On the left, you have the virtual objects without filtering, and on the right, you have trilinear filtering in mip mapping. Right, so you can see here in the back, you can see aliasing. So here you can see chessboard pattern, and here in the back, you get wavy lines here. That's a typical aliasing artifact. Also, when you look at the edge of the sphere here, it looks noisy. So it doesn't really look like regular pattern anymore, but more noisy. And when you look on the right-hand side, here in the beginning, it looks a little bit less sharp, so that's not so good. But here in the back, you don't have those alias effects anymore. So here, this looks unsharp, as it should be, to avoid those wavy lines, which are artifacts. And then here, the edge of the sphere also looks cleaner now, less noisy. Yeah, so now in Python OpenGL example. In Python OpenGL, we can create textures procedurally. For instance, a fractal like the apple mannequin from our lecture 5, or simply read an image from a file. So here's an example for reading an image from a file into the texture array image. So here I'm using OpenCV to read the image. Here, this is the texture file, tui.png. This is read into image. OpenCV gives a little different coordinate system than OpenGL expects, and that's why we need to flip it here. So we flip the first axis to get the same coordinate system, or the system that OpenGL expects. And here we can see the shape, the dimensions. So here we have the x dimension, the y dimension, and here the number of primary colors. Here's an example for the procedural creation, in this case of the Mandelbrot set, the apple mannequin from lecture 5, into texture array image. So here you can see I'm initializing the image here with zeros, 512 by 512 by 3 primary colors. And yeah, so this is then also given to the indices for the for loops. So these are the index ranges, and here you can see I have 2 for loops for each dimension 1. So here for the x dimension, here for the y dimension. And then I'm doing here another for loop for the iteration for the Mandelbrot set. So here with this for loop just going over 10 iterations, which is not very much, I can detect how fast it is diverging or converging. Right, so here I have my iterations for the Mandelbrot set, each time starting at z equals 0. Here is the starting point for the iteration in C, and this depends on the current coordinate. So here you can see x is the index of the x for loop, then here y is the index for the y for loop. Here I have a normalization to make it range between 0 and 1, and here I'm subtracting 0.1 so that I have a complex value which is between, this is between minus 0.5 and plus 0.5. I multiplied by 4, so this goes for between minus 2 and plus 2 for the real part, and this goes between minus 2 and plus 2 for the imaginary part. So C is then our starting point a complex value in the range between real and imaginary -2 to +2. And depending on the starting point, we have different convergence behaviors. And here I'm estimating this convergent behavior. So after I'm done with this for loop, I'm looking at the magnitude of z, the resulting z, and I cut it to the maximum of 200. Right. So everything above 200 means it really diverges a lot. So I don't distinguish that anymore. Here I normalize it again and scale it to 255, so that MA is working like a color byte. And this is actually taken for primary color 0, which in this case is, I think, the red channel. So this should appear red. Yeah, so we have the choice of those two images, and then we can map them on our object, which is done in OpenGL using this command here. So here we have GL text image 2D. This defines a texture, 2D texture. Here we have the image coordinates. Here we have the ordering of our primary colors, blue, green, red. So this actually corresponds to what OpenCV generates. Here we have the type of our texture, unsigned byte. And here's our texture array. Yeah, and next we need to define the type of mapping and interpolation of the texture pixels to image pixels. And this is defined with this command, GL text parameter f for float. And here we can choose the type of filtering. So here is with nearest neighbor, which is called GL nearest, which you can see here as an argument. So this uses nearest neighbor filtering. And here's the alternative bilinear interpolation, GL linear. So instead of GL nearest, we have here GL linear. And we also need to turn on the texture at the beginning with GL enable GL texture. Yeah. Then we need to define the area of the texture. So this is basically the mapping of the texture to our 3D object. And this is done with GL text coord to F. So F again for float. So this connects the vertices with the corners of our image, our texture image. In this way, the UV coordinate system of our texture image is mapped onto the coordinate system of our 3D object. Example for an image point to a vertex is given here. So here we begin the definition of a polygon, right? And here you can see the first vertex. So here GL text coord 2F. So this is the coordinates of the first vertex, and this is connected to the texture, pardon me, so this is the texture coordinates, so this is the one corner of our texture image, and here we connect it to the vertex coordinates. So here you can see the 3D coordinates of our vertex. So this point in 3D is connected to the local 2D coordinates of our texture here. And we do that with all the points of the polygons. So you can imagine we repeat this process for each vertex of our object. Yeah, and here it's useful to have the color of the polygon first set to a medium value so as to not overpower the texture. For instance, 0.7 here, right? Yeah, and here we have two examples. First, a simple wire polygon with texture, and then we have the same simple wire polygon with a fractal texture. So let's try it. So first let's take a look at what's inside. Yeah, so it's already open here. So this is wire polygon texture. So here we have the display function. So this defines our virtual camera as before. And here now we have our object. So here we still have the camera, and here we begin with the polygon and texture coordinates. Here the color, GL color 3F, so here you can see the 3.7s. So this is a medium gray value. And here I define a polygon, which you can see here, begin polygon. And here I'm defining the connections between our texture coordinates 0, 0 to the first vertex, -1, -1, 0. Here the next coordinates 1, 0 to the vertex. So I have 1, 2, 3, 4 vertices and correspondingly 4 points in our texture, which I make the connection here. So here you can see I can define or connect all 4 points of our texture image. Remember, the texture image has coordinates between 0 and 1. So here you can see it accordingly. Yeah, so here I defined our object with a connection to the texture. Here now I have my main part. So here I'm creating the image, right? Display mode. Here I'm enabling the texture. GL enable GL texture 2D. Here I'm setting the color of our window background. And here I'm reading the image. So this is the TU Ilmenau logo. Here I'm doing the flipping to get the right ordering of the coordinates. And here I get the coordinate range. Here I'm defining the mode. Here we have the BGR for the primary colors, unsigned byte, and here I'm connecting the image array to our object. So here this is the image array which I need to read in, and we just read it in here. So now it's used for our 3D object. And next I'm defining the way I'm mapping it, using here GL nearest first, and then I display it. So let's try. So via polygon texture, Python 3. Yes, so here you can see it. This is our window, texture polygon. Here we have the background color of our window. Here we have the default color of our polygon, this medium gray, as you can see here. So this also makes it visible in our background here of our window. And here's the logo that we read in, right? This logo now using a nearest neighbor filtering, and when you actually zoom in, which is actually not really possible, you can see little edges here. And this comes from this nearest neighbor approach, the little sawtooth edges. Let's see what happens if we now switch to a bilinear filter. So I'm commenting out GL nearest and go to GL linear. So let's see what happens. So now we have the same with a bilinear filter, and when you look closely here at the edges, this sawtooth pattern is gone. So now the edges here are really clean. So they don't look as edgy anymore. No little sawtooth. So you can actually see it when you have you can actually see it better if you have a high resolution display and look closely here, that the edges are displayed more cleanly if we have this bilinear interpolation. So it shows you that it's actually advantageous to use this bilinear interpolation. So that's kind of nice. So here's then our next example. So the Polygon fractal texture, via Polygon fractal texture. So first let's take a look at it. It's already open in my editor. So basically it's doing the same thing in the beginning. So everything is the same. Here background color of the object, here the connections of the image coordinate system to the object coordinate system. Here I'm starting our window with white as the background. And instead of reading in the image, I'm now creating the image, this texture image of the Apple mannequin. So here you can see the two for loops for the coordinates of the image, and here this inner for loop for the computation of the fractal. Yeah, so here you can see it, and this should be the red channel, I guess. The rest is the same again. Here we're setting up the texture with the image of image array. Here we start with nearest neighbor, the cheapest version kind of, and here we display it. So let's try it. So instead of via polygon texture, I'm now taking fractal texture. And you can see it takes a few seconds because it first needs to compute our fractal. And you can see here's the result. And again, here, since we have nearest neighbor, when you look closely at the edges, it has this slight sawtooth pattern here. So the edges are not so clean. And if we switch to linear, bilinear, GL linear, then the edges should appear more cleanly. So again, it takes a second or so to compute. And here we can see now this sawtooth pattern here at the edges disappeared. So the edges are much cleaner now. And this is particularly important for high resolutions. Yeah, so that shows it works. And bilinear is better than nearest neighbor. Okay. Yeah, and this can also be used for the so-called displacement mapping. The objective here is the representation of a three-dimensionally structured surface. So say you have an orange or something like that, then you have those pattern on the surface, or the surface is kind of rough. And you can represent this as a pure image to give it the appearance of this roughness, but you can actually do more, and that's the goal of displacement mapping. So the idea here is to influence the geometry of the surface by displacement texture. And the texture then controls deviation of the geometry from the default. So the default might be the sphere, and if you want to represent an orange, then you want to actually have small deviations from the sphere in order to represent the texture of this orange. Realization here, the grayscale image contains the height information which the geometry is modeled with. Right, so basically when you have high brightness, that means you move your object a little bit outward, and if you have dark value, you move it a little bit inward, for instance. Advantage here is that you have a very good rendering even at short viewing distances, right? Because there you could see if it's just an image or if it's really there. Disadvantages here, it requires high resolution mesh, meaning one vertex per texture pixel or per image pixel. Obviously, because if you want to move a vertex for each pixel, you need to have a vertex for each pixel. And that means you have a lot of vertices. And the original implementation requires adaptive tessellation to get to this high resolution. So this shows displacement mapping. Here's the grayscale image. Right, and so for instance, you want to represent a keyboard with just an even surface, and then you want to model the keys just using this displacement map. So you have this grayscale image as a displacement map, and when you have dark gray or black areas, then you go a little bit inside, and if it's bright, you go a little bit outside. And in this way you can model the shape of the keys. Yeah, so you move the vertices to the new geometry. So you really need to have vertices for this to work. And this is then the resulting three-dimensional structure. Then we have bump mapping. So the objective here is the representation of three-dimensionally structured surfaces. The idea is to create the impression by modeling the surface normals, right? And this needs Fung shading, which we will see later. The advantages are that it's less computational complex than displacement mapping, and it's independent of geometric resolution. And what we do here is actually we just change the way that our virtual light is reflected from the surface. So it looks like there's a pattern on the surface by the way that the light is reflected. And we do that by changing the surface normals. The surface normals are determined to compute how light is reflected. And this can be done, for instance, with a Fung shading. So it's kind of cheating. It just looks 3D, but it's not really 3D, but it has the advantage that it's much easier to compute. And hence it provides good results for medium and large viewing distances. Disadvantage is it has no self-coverage. So if you go close to, say, the keyboard or the surface of this orange, you see that there is no real pattern in this case. So here's an example. Here you have this torus, smooth, and here you have your texture, and after projecting the texture on this torus, you really get the impression that it looks like a snake, for instance. And that's the way the light is reflected here. You can see the shadows, and those shadows give you the impression that there is really this pattern on the surface. So in bump mapping, we have the coding of the normal vectors as color image, because the normal vectors have those three components. Usually we have a representation of the X, Y, Z components in the color channels red, green, and blue. And for this we need a scaling into the positive value range of the RGB representation. Right? So X, Y, Z can be positive and negative, but RGB is always positive, hence this mapping. And we can also, in this way we can create a displacement map, and we can also use it to create like a procedural texture. So we already saw procedural textures with our Apple mannequin. So in general, this is an automatic generation of texture using an algorithm. This is well suited for repetitive patterns like a chessboard, for instance, or fractals like our Apple mannequin, and also useful for more complex algorithms, which are well suited for natural materials like concrete, stone, marble, wood, leather, fabrics, and metals. So here you need complex algorithms because you can clearly see the pattern which is characteristic to a certain material like marble or wood. So here you can see examples. So here you have those procedural textures for the same objects, and in this way those same objects look like they are of different material. Like here it looks like concrete, here it looks more like marble, here more like bronze, and this might be copper, for instance. So here you need those sophisticated algorithms to create those patterns. And this is basically also volume textures. These are textures that assign a color value to each point in the volume of an object. So not just the surface, but the volume. And they are often executed as procedural textures because that's easiest to make a 3D texture. It's kind of hard to take a picture and make it 3D. They are often executed as procedural textures, right? Well suited for objects that are cropped, like wood, stone, and so on. And they look very realistic, but they have a very complex calculation. And that should be it for today. Thank you for your attention, and then see you next time.